part of a quantum error correction. We started this thing, which was kind of a basic for what can be the different errors that can happen due to like decoherence and other stuff, and which is also a fundamental thing for uh, different aspects of quantum computing, the quantum error correction. Followed by that, we have seen what are possible types of error that can happen in classical communication, where we have seen the different kind of like checking thing, like parity checking, then redundancy bit adding kind of technique that we generally used, just like in our standard CRC or cyclic redundancy checking scheme. So we all have seen these things and we all know also part of it. So today, and post that, we also have seen a very fundamental error correction scheme, which was a 3-qubit error correcting scheme. But 3-qubit error correction is based on only the bit flip error, where we believe that in a quantum state, only the bit flipping, the error can occur due to only the bit flipping criteria, where maybe 0 can be 1 or 1 can be 0. But what might also happen was at end of 3-qubit, we have seen that there can be also a possibility of a phase flip error. Phase flip means your phase of a particular quantum state that also can be changed. So in that case, 0 will be mapped to 0 because plus 0, minus 0, both are same thing. But plus 1 can be mapped to minus 1 and vice versa. So on these two, like the situations where both the phase flip and the bit flip can happen, we have seen one advanced form of quantum error correction algorithm, which is called the Shor's 9-qubit error correction scheme. Now, in that algorithm, we have seen that why it is called the Shor's algorithm, Shor's 9-qubit algorithm, because it was discovered by Shor. And why we call that there is 9 qubits, we have seen that 2 ancilla qubits were added or are added at each step with respect to each of the 3 qubits. That is why it is called the 3, like 1 plus 2 plus within bracket 1 plus 2 plus within bracket 1 plus 3, which is nothing but 3 plus 3 plus 3 is equals to 9. So all these 9 error correction qubits are there. And also we have seen that why it is not 3 into 3 into 3, because the circuit, if you see for Shor's 9-qubit error correcting code or error encoding code, it was a kind of an independent one, where each subunit comprising of 3 qubits were totally independent. That is, first subcircuit was independent of the second and that of the third one. So there is no multiplication, rather there was addition. It was of an additive nature. These things we all have seen. So where exactly we paused in the last class was, we were supposed to start error decoding of Shor's 9-qubit circuit. So today we will start with that. Once we end that, we will enter into a bit of the theoretical descriptions of what is the introduction to classical cryptography. So this is so far of a plan that I have put here, what you can see in the further today's agenda. So post that, we will see how and why and what kind of quantum threats we can actually face with respect to the classical cryptography. Post that, it is a quantum resilience in cryptography and why it is very important. Okay. And then once the resilience is understood by all of us, we will enter into the post-quantum cryptography, or what are the schemes for that. This is so far what I have targeted for to cover in today's class. Okay. I hope all of you, who have attended the last class, we are on the same page. So we can start with the 9-qubit error decoding circuit. Just give me 1 second. Yes. So I don't assume that I have to again draw the circuit that was from the initial circuit itself. So for that, I have initial part of the today's lecture, I'll be using a whiteboard. Post that I'll be using also slides today. So first part was from where we left, that is, just give me a minute. So it is a error decoding circuit. So it is error decoding in Shor's 9-qubit, this thing. So just note that in our these 3 days, we are not only covering quantum cryptography, but also we are covering the quantum error correction, not the basics or fundamental of error correction. Okay. These two are very much entangled. So I thought of covering this part as well, along with the cryptography. Because classical cryptography, we can have a good place in that because we all know that one. And tomorrow my target is to cover the quantum cryptography followed by some of the future research directions. And whatever is the technique there, we will be covering. That is my plans for today and tomorrow. So error decoding is, if you remember, I will not draw the earlier circuit of this one. If you just remember, we had this kind of a stage where we paused our discussion. So we had this step followed by the probabilistic calculation. We have seen that the probability of multi-qubit error is very less for that of Shor, which is an improvement of Shor with respect to the 3-qubit error correcting code, because in 3-qubit error correcting one, there was a 50% of chances for getting an incorrect state, and which is exactly similar to that of chances of getting a correct state. But for Shor, no error and only one error is more probable than 2 or more number of errors. So considering that one and thinking or considering it to be an improvement, we are followed by this concept. Voice is low, trying to be louder. It may be because of I have an issue with the voice, but I'm trying to be as loud as possible. Yes. So I will repeat if you're having any issue. Okay. So this was the last step that we had. Okay. In yesterday's class, we ended here during the circuit expansion and all. So now we will go for the decoding phase, where it starts with an assumption that say out of the 9 qubits received, we have a single qubit error, and that error has taken place in only the first qubit. Okay, just one quick question. Is my screen exactly visible? Is it the issue with only 1 or 2? You already can see some of the comments. It's visible. Thank you, Dilip. For rest, voice is also proper. Okay, thank you. So let me just continue. So this is the stage. So now I'm assuming, so what my assumption is that out of 9 qubits, out of those who are having an issue, just try to rejoin and let me know if the issue still persists, then I will try to also join. Maybe, but that will actually take away 1 or 2 minutes or hours. So just try to rejoin. Otherwise, I will again try from my end. So out of 9 qubits received, okay, out of 9 qubits they received, now we are assuming that we have a single qubit error. We have a single qubit error, and that error has taken place in first place. Got it? And what kind of an error? We are assuming a sigma y error. What is a sigma y error? If you remember, it is a combination of flip as well as a phase flip error. Okay, let me try. Just give me 1 minute, let me again try. Just give me 1 minute, let me again try. Let me try. So I'm again trying to I'll leave the webinar and try to again join. Just give me some seconds. Now again try. So let me know the status. Now voice is okay and okay, okay, okay. Thank you, thank you. So, so this was the state where we ended in yesterday's class. Just a quick recap. Then now what we are assuming is out of 9 qubits that we have received. Okay, receipt means at Bob's end, we have a single qubit error. Only in 1 qubit we are getting an error, and that error has taken place in the first place. What kind of an error we have got? We have got a sigma y error, which means a bit flip error, as well as a phase flip error. Now we will be applying the effects of both the errors on these obtained state and see how it becomes like. So first, if we apply, if we apply a bit flip error, which is a sigma x on the first place, first qubit. So it will become this thing. 0 will become now 1. So 100 plus 011 divided by root 2, and all these things will be intact since only it should be affecting the first place. Plus beta times 100 minus 011 divided by root 2 into 000, only bit flip, no effect of phase flip. Here, I have got it. Sorry, this was minus. Yeah, divided by root 2 into 000 minus 111 divided by root over of 2. This is the thing. Now I am applying what? The effect of phase flip error. So phase flip error, or say sigma z, will make it what? What it will make? It will make my phase, it will change the phase of it, okay, of the first position. That means it will make this one as a 100. Only in these two positions will we see a significant change. All the other things will be intact. So this one will be minus 011 divided by root 2, and this is 000 plus 111 whole divided by root 2, 000 plus 111 whole divided by root 2 plus b into the just the reverse, that is 11100 plus 011 divided by root 2 into 000 minus 111 divided by root over of 2 into 000 minus 111 whole divided by root 2. So this will be the error or the resultant state after both the things. Now, what is our ultimate purpose? See, our ultimate purpose is, our purpose here is to encode, so 0 into logical 0, this thing which is nothing but plus plus plus. That is how we have encoded, or we have seen that how to convert computational basis to the diagonal basis. We have seen this thing yesterday, and also like H1 into logical 1, Kate of that, which is minus minus minus. This is what we want to encode is. Okay. Now the decoding circuit, let me draw the decoding circuit. So the decoding circuit will look something like this. See, very strategically, I am just drawing it so that you also be able to identify how the circuit is made up of. So I have 9 qubits, right? So let me start with Q0, Q1, Q2, make it a triplet, then Q3, Q4, Q5, make it a triplet, then Q6, Q7, and Q8, and make it another triplet, third triplet. Now, very similar kind of an operation I'll be doing on all the triplets. Very similar, like the same fashion I'll be applying a series of quantum gates. The first quantum gate for this one is a C0 gate from Q0 to Q2, then a C0 gate from Q0 to Q1, okay, then a Toffoli gate or a C-square NOT gate where Q1 is the control and Q2 is the control, and target is my Q0. Okay. Similarly, the exact same fashion will be repeated for both the triplets or both the units, say. So Q3 is the control, Q5 is the target. Here Q3 is the control, Q4 is the target, and here Q5 and Q4 are control, and Q3 is my target. Similarly, here Q6 is control, Q8 is target, Q6 is control, Q7 is target, and Q7 and Q8 both are my control, and my Q8 is the target. So these are independent execution that I can perform. No such one triplet is dependent on the another part. So here Q0 is now will be fed to a Hadamard gate. Q3 also fed to a Hadamard gate, and Q6 also will be fed to an Hadamard gate. And the output, let me just draw the output line like this. Now in this subspace, again, I'll be following the exact logic that I have done on any of these triplets. So out of these 3 qubits now, say this one, and this one. So it will be Q0 to Q6 on their output line. It should be a C0. Then Q0 to Q3, it should be it should be a C0. Then considering Q3 and Q6 both as sorry. So Q3 and Q6 both are controlled. There will be a target at Q0. And this is the final output. Okay. So what are the list of operations? Let me just write it down. I'm not getting this one. Let me just change the color. So first operation that I have to do is C0, Q0, Q2. Second one is C0, Q0, Q1, followed by third is C square naught or Toffoli, whatever you say it. Toffoli, Q1, Q2, Q0. This is control, this is control, this is control. The remaining is the target. Fourth operation is C0, Q3, Q5. Fifth one is C0, Q3, Q4. Sixth one is C square naught, Q4, Q5, and Q3. Where logic is, it will work only when both the Q4 and Q5 is 1. Then only flip Q3, and here also it is both when both Q1 and Q2 is 1 or R1. Then just flip your Q0. Similarly, the 7, 8, 9 gate are. These are all the list of sequential gates that you have to perform on the earlier obtained quantum state. So it is a C0 gate on Q6, Q8, followed by C0, Q6, Q7, followed by C0, this thing that is Q7, 7, Q8, Q6. Till this part. Till what part? Till this part, this is all the effect of 9 operations. Suppose that there is, after this step, there is a list of 3 Hadamard gates. So you will do it sequentially, and then followed by again some 3 C0, C0, C square naught, this triplet of operations we have to perform. So let me just draw where we ended. Draw means write down let me write down the state where we ended. So it's 100 minus 011 by root 2, and this is 000 plus 111 by root 2, and 000 plus 111 by root over of 2, plus this is b into just the reverse, that is this thing that this is 100 plus 011 by root 2 times 000 minus 111 by root 2 into 0, 0, 0 minus 1, 1, 1 by root 2. Okay. Now I will not write the detailed step here. This is very easy. All of you should be able to do it by yourself. So once I apply all the 9 operations, just for your simplicity, let me tell you, this is Q0, Q1 and Q2. And this is also Q0, Q1, Q2. Similarly, here also this is Q0 for B, Q1 and Q2. This is Q0, Q1 and Q2. Now, of course, you are understanding that this means this is your Q3, Q3, and let me write in this way, and this is your what? Q3, Q4, Q5, Q3, Q4, Q5. And similarly, this is your Q3, Q4, Q5 minus Q3, Q4, Q5. And this one is your Q6, Q7, Q8. This is also Q6, Q7, Q8. Similarly, this one also, like Q6, Q7, Q8, Q6, Q7, Q8. Okay, now from 0 to like Q0 to Q8, all the 9 qubits are actually in this way. They are listed, or say they are positioned in the composite quantum state. Now, on this note, if I apply all the like C naught and C square naught operation based on what is my Q0, Q1, Q2, Q3, all these gets, now we understand it. So once you do that, you will be getting the resultant state as, say, A, then 0, 1, 1, 0, 1, 1, minus 1, 1, 1 by root 2. And this will happen 0, 0, 0 plus 1, 0, 0 by root 2 into 0, 0, 0 plus 1, 0, 0 by root over of 2 plus b into this thing, that is 0, 1, 1 plus 1, 1, 1 by root 2 into 0, 0, 0 minus 1, 0, 0 by root 2 into 0, 0, 0 minus 1, 0, 0 by root over of 2. This is an application of all the 9 operations. Okay, C naught, like 1, 2, 3, 1, 2, then 3 is remaining 1, 2, 4, 5, and 7, 8. These many C naught, and at 3, 6, and at 3, 5, and 8, we are applying, say, I guess 2, 5, and 8, we are applying C square naught. After this, we are getting this thing. Okay, now just for the sake of, just now, what is the next step? Just see the circuit. We are in this phase, completed 9 operations. Now we should be applying Hadamard gate. On which thing? On the first, that is Q0, on that is fourth, that is Q3, and that is, say, next one, which is Q6. So on Q0, Q3, and Q6, we should be applying Hadamard gate. Now, if you see these particular structure, like getting the first qubit and applying on Hadamard is little complicated, because this is also like your Q0, this is also your Q0, this is your Q3, this is your Q3. And since we want to apply only on Q0, Q3, and Q6 for both A and B, let me just write a like alternate representation of this particular equation. So which will be, as a result of, say, rewriting this thing in our comfortable way, it will look like, say, A. Let me just take right hand side 1, 1 as common, so it will be this thing only. I hope all of you agree. Okay, if you give a bracket or not, that is irrelevant. If you give a tensor product or not, that is irrelevant, because for our representation purpose, so this will exactly look like that. Okay, the first one followed by, so similarly I will be writing all the steps. Say, this thing times, it should be 0, 0, followed by h0 plus h1 by root over of 2, 0, 0. This is done. Now this one also will be similarly h0 plus h1 by root 2, and this is 1, 1 times h0 minus h1 by root 2. This is 0, 0, and this is h0, same thing, minus h1 by root over of 2. and 0, 0. Same thing, both the steps are exactly same, just the alternate form. Now I have to apply what? I have to apply 3 Hadamard on which gets Q0, Q3 and Q6. Now what is my Q0? It is my Q0. This is Q3. This is Q6, just written in a composite way so that it's easier for us to apply the Hadamard. This is Q0, this is Q3, and this one is your Q6. Okay. Now, respectively, in these positions, I have to apply Hadamard. So, if I just apply it, say just one thing, let me write it down. So, Hadamard on Ket0 minus Ket1 by root 2 is what? It is basically Ket1. If you remember, Ket1 when passed through an Hadamard, it produces this thing, Ket0 minus Ket1 by root 2. Since two Hadamard get working in this way is nothing but an identity one. So again, if you pass it, we'll be getting the same one, which is 1 will be carried out here. Similarly, Hadamard Ket0 plus Ket1 by root over of 2 will be your Ket0. Because Ket0 when passed through a first Hadamard, it will make it Ket0 plus Ket1 by root 2, which is represented by 1, 1, taking 1 by root 2 as common. If it is again passed through Hadamard, I will be getting a Ket0 itself, which is 1, 0. Okay. Now, if this thing is exactly now written, so now say after applying H Q3 Q0 H Q3 and Hadamard of Q6, what I get is this one will be now become Ket1. So it's A Ket1 1 1. Likewise, right? So now if I just write it down, it will be A then 1 1 1 plus 0 0 0 plus this thing which is 0 0 0 plus B is 0 1 1 plus 1 0 0 plus 1 0 0. Okay, this is what I will be getting. Now the thing is that now what are the three gates where we want to see some result? See here, we are not really interested. If you just see the circuit, we are not really interested with what is the status of Q1 and Q2. Once this step is also done, we are not really interested to see the status of Q1, Q2 or Q4, Q5 or Q7, Q8. So instead of writing them, let me write a simplified version of this where from each of these states, I will be only taking the first one and make it one state. So this one, and this one I will be taking and frame one state which is say uh, ket 1 0 0. Okay, let me remove this one. Yes, so A 1 0 0 plus B ket similarly from this 0 will come, from this 1 will come, and from this 1 will come. So your A 1 0 0 plus B011 is your resultant state after Hadamard. So this is your state after all three Hadamard. Are we ready for further calculation? Yes. Why? Because now let me just draw it here. So it's a A100 plus B011. Now where this is Q0, this is Q3, and this is Q6. Similarly, this is Q0, this is Q3, and this one is your Q6. Why I am doing it again? Because on these three qubits, we have to perform the next step. What was the next step? Let me check in the circuit itself. It was a few more C naught gate and C square naught. So what it is? C naught, Q0, Q6, C naught, Q0, Q3, and C square naught, Q3, Q6, Q0. So the gates now I have to apply is, now the sequence of gates are, C naught, Q0, Q6, followed by C naught, Q0, Q3, where Q0 is control, Q6 is target, here Q0 is control, Q3 is target, then a C square naught, a Q3, Q6, and a Q0. So this one will become what? Let me just write it down. So after this operation, it will make it from this step I'm getting. Okay, this was my state. I'm getting what? A, I should be getting 101. Just check it. This one should make this one as 1. So 101 plus B 011. And this will be 111 plus B 011. And this one will be 011 plus B 111. So this is at end what we are getting. Okay. So this one I can write in this way, that is A get 0, which corresponds to Q0, plus B get get 1 corresponds to Q0, this Q0, like this thing and this thing, times get 1, which is Q3, get 1, which corresponds to Q6. Q6. Okay. Now, get 0 was thought of to be get 000 plus 111. Tensor product 3, where I'm just not writing the 1 by root 2 term here. So ignoring 1 by root 2 and all these things. That is the amplitude. And ket 1 is nothing but 000 minus 111. This thing. Okay. Now, say a bit flip has occurred. So now we are interested to know on which qubit the error has taken place. So the decoding mechanism, this is what we are aiming for and for which we are doing all these calculations. So now we just want to calculate the bit flip error and where it had occurred and why it had occurred. All those things. We want to analyze it. Now say for example, that is we want to measure, say a bit flip has occurred. And now we are interested understand where the error, where means on which qubit, basically which qubit the error has taken place. That is a question. Once we have that, say first compare. What to compare? The parity. So please check your parity between 1 and 2. So compare 1 and 2. That means sigma Z1 and sigma Z2. Just compare them. And for another comparison, say check parity of, say compare 2 and 3, which is true sigma Z2 product Z3. Okay. Now based on the outcome, see what outcome I can get out of these two equations, say 1 and 2. So from 1 is sigma this thing. So this result can be either plus 1 or minus 1. Because each of the values can be either plus 1 and minus 1. Similarly, for equation 2, I can get Z2, Z3 also same plus 1 and minus 1. Now, let me draw a table where I'll be writing both the values. Say sigma Z1, Z2, this is first column, followed by sigma Z2, Z3 as second column, and here it is my decision. Okay, now say here I'm getting a plus 1 and here also I'm getting a plus 1. When can both the values be plus? When Z1 and Z2 both are plus, this is plus 1 into plus 1, that is plus 1. Similarly for this, so individually that also means that nowhere I have got any error. So this is a no error situation. Now say here I have got a +1, but here I have got a -1. Now when I can get a +1 for sigma Z1 product Z2 when both are 1 +1. Now here I am getting a -1. That means Z2 has to be 1. Now Z3 has now become -1. Whenever this will happen, we'll understand that there is an error in bit number 3. Okay. With the similar logic, if this is -1 and this is +1, we will call there is an error in which bit? Bit 2. Okay. Sorry, not in bit 2. It is in bit 1 because Z2 and Z3 both has to be +1 in order to get this one as +1. Now, if I get say -1 and -1, it has to be the main culprit is which is making both the values as -1 is error in bit 2. So this one will be mean error in your bit number 2. Okay. So this is the thing which you should be remembering. And also say now, say there exists a phase flip error as well. For that, what you should be doing it, let me take it in this way. All these three triplet wise we will be taking from 0 to 8, that is all these values. This is one set, this is another set, this one is another set. Now, whenever I say 1, now instead of like unlike bit flip where we are considering each of the qubits, here we will be considering the entire set as 1. So this is 2 and this is 3. Now, whenever I say compare 1 and 2, you will be doing this 1 and 2 comparison, that is Q0, Q1, Q2, Q3, Q4, Q5. All these 6 values you have to compare. Okay. And whenever I say compare 2 and 3, I'm just repeating it. So for a phase 1, you will be comparing instead of a particular say single value, you will be considering the value in terms of the entire composite one. Whenever I say compare 1 and 2, you actually have to compare what? Let me just write it down. So for this thing, you have to compare for 1 and 2. This is not qubit 0 and qubit 1. Rather, it is what for 1 means it is Q0, Q1, Q2. And 2 means it is Q3, Q4, and Q5. On this comparison, it will means that you have to now compare in terms of blocks. In terms of blocks, not bits. Now, if you compare them, what you will be getting, what you have to actually compare all these 6 values. So sigma Q0, sigma Q1, sigma Q2, Q3, Q4, Q5. Compare this thing. Okay. And compare 2 and 3 means now instead of unlike the bit flip 1, here we have to compare. This is Q3, Q4, Q5, and so something like this. This is Q3, Q4, Q5, this is Q6, Q7, and Q8. Because it is, the 2 means it is a block of these 3 qubits. 3 also means it's a block of these 3 qubits. So it will be that one, the case. So it will be sigma Q3, sigma Q4, sigma Q5, sigma Q6, Q7, Q8. All these values you have to check. Okay. Now, if there exists a phase flip, we can correct using, if there is any phase flip, how we can correct it? We'll make the reversible. Quantum is a reversible operation or a computation. So we'll be applying a sigma z, which is nothing but this matrix. And on application of that, it will make your sigma z will make your 1 0 to be 1 0, and it will make your 0, 1 to be 0 and minus 1, which is sigma 1, sigma 0 is 0 and sigma 1 is minus 1. So therefore, if we have both phase flip and bit flip error, then each error can be sequentially taken care of. This is the logic. Okay. And this is the end for our discussion for the Chords 9 field error correcting one. And now we will enter into what? The discussion of the cryptography. That is our agenda. I'll be writing all these things. Let us go back to the slides. This is where we are in need. Just we have not used these slides. Now, so before starting it, let me just create, instead of directly jumping into classical cryptography, let me give you a brief intro of why this is a very booming field. It should give us a platform because in our very first class, like day one, we discussed a few of the pitfalls that exist with respect to our classical ones, like the time complexity for the TSP problem and the computational explosion of the search space. We discussed all these issues. Also for the space complexity, we have seen that that is also another challenge which we cannot really not consider further. Just like a few of the cases of pharma, where the protein folding problem or that much of all the possible configurations of amino acids just to encode them or store them in memory, it will take a lot of time. Simulation inefficiency was another one because we cannot go into the quantum level in order to do a perfect simulation or a perfect measurement because of the contextuality and non-contextuality that both of them exist in quantum. It's perfectly natural system. And we also have seen that like precision and efficiency, all the stuff were also another error stuff. So all these things we already have discussed. Now, all of them actually belong to the domains like optimization, machine learning, simulation and modeling, all those stuff. What area was the area that was completely unexplored in terms of the pitfalls was cryptography or cybersecurity space. Now it is not really very kind of a non-trivial to mention that cryptography is used in everywhere, right? Cybersecurity, all the protocols, all these things are used everywhere. Now, concept is why this is very important and why this is the primary pitfall where you can get a real traction right now. If you just want to do something right now, you can actually show something. I will discuss those aspects as well, try to discuss because today we will not enter into quantum cryptography, so we will only be discussing. This is how I will be spending time. If I get some time, then we will talk about a bit of entropy and mutual information and maximally entangled state. All those things also. Okay. So, why this was very interesting is again a quick like intro. This one line I am telling in all these days and all these lectures is the Schwartz cryptographic algorithm, which is thought of to be a threat. Now, the threat was how adverse the effect can be. Also, I've told you that with the help of Schwartz algorithm, what we cannot do right now with cryptographic algorithms is because of the inherent complexity of the factorization problem. Factorization problem means if we have a very, very large number, and if we are asked that what are its two factors, say prime factors, we cannot determine it in terms of which two factors comprise of our public key and a private key. So similar logic, was used so far for most of the cryptographic algorithms that we can see has a maximum number of applications. Okay. But Shor came up with a solution known as Shor's algorithm, which uses quantum Fourier transformation. And he had shown that, okay, if you give 15, the number 15, then it has shown that with respect to Shor's algorithm, it can actually break it into the factors 3 and 5. Okay, that is the essence of Shor. Now you will say, you will tell me that 15 is not a really a real number, then why should we be worried about? We should be worried about because the machine is ready. Say, for example, in this year, I do not have a much of a production of rice, but my rice mill is working properly. I have enough of fun. Just the introduction. I'll repeat everything. Just consider the story. Just hear the story. Say, for example, what I just had said is Shor algorithm using quantum Fourier transformation has already broken the RSA cryptographic algorithm with respect to a small example. If you give, say, 15, it has already broken into 3 and 5. This prototype has already been designed. Also for another number, say 21, 3 into 7. Those kind of things we already have seen in the real quantum computer. Now you might be asking me the question that in reality, does really RSA or all these currently used cryptographic algorithms, do they really use this much of a small number? Maybe Shor has broken 15, but if it is 15 lakhs, then Shor will not be able to break it. Absolutely, the logic is this one is correct. But the thing is that now just consider an example of, say, I do a trading with kind of a rice, say farmer or something, anything. I have a rice mill as well. I'm a very rich farmer. I have a rice mill. I do it from the like end to end kind of thing. But this year, for some reason, I do not have much of the kind of a production of rice. Okay. Does it mean that I, in the next year, cannot produce it? Once I will be having a good production of rice, I can again do a very like good amount of business. That definitely will be taking place. So similarly, here also the machines are ready. That is the thread that we all are right now bothering about because the machines are ready. So how it will be doing it, what it should be processing, how it should be processing, all those mechanisms are perfectly ready. What we want is just some rice, that is some non-erroneous qubits or a strong quantum computer and a new input which is significantly higher. Once I have that, my machine, which is say Shor's algorithm is nothing but a machine works with, say, it at least generate one output, even if it has no input, kind of that, if it is an automated machine. Similar to an algorithm is a fundamental criteria of some logic to be an algorithm is it should be able to produce at least one output, even if it has zero or more number of inputs. So definitely that kind of algorithm or logic is ready to be with Shor. So, and the big number is also ready. What we want is just the more powerful set of quantum bits or say a more powerful quantum computer or noise resilient quantum computer, whatever you say. So these are all the things that we require. Now you understand the threat. That means someone is ready with everything. Just the value and the like bit of the research is pending. So this is the fastest paced research that is going on. Because of the security, it is used in everywhere. The most promising application areas are banking and finance, say pharma, say some personal health records. These are a few areas where it is very, very much confidential and entire blockchain. It works on these kind of RSA and all these asymmetric algorithms. Those are also important. So that had actually opened up a new dimension of cryptographic, say, study, which is called as a quantum cryptography and also a post-quantum cryptography. So this is our agenda. So for the next 1 hour, we all will be discussing about this. Okay. Now let me give you 1 or 2 minutes of break. Just I also want to have some water. Once we are back, we will enter into the classical cryptography. We'll start this. So right now is 2:57. So we will exactly start at RS and others are there to secure. So why crypto is important? No, they are not secure. RS and others are not secure. And if we are unable to give some sort of theoretic security, we cannot right now claim it to be secure. So in classical physics and everything, because of quantum, absolutely, because they are not theoretically also very secure. I will be discussing just right now it's 2:57 or 2:58. We will exactly start at 3. Let us start at 3. We will be discussing only. Not be using any whiteboard today further. If time permits, only for the mutual information, maybe 5 or 10 minutes. Before that, we will be only discussing problems. Okay. Let us all come back after 2 minutes.
Yeah, thank you, ma'am. One small announcement. I have seen that only about 400 people have taken the test. Taking the test is very important. Kindly note the point. So it's very important to please ensure that all of you take the test. Please inform your friends also. Here at least we have 456 attendees, and about 50 of you may not have taken the test. That means, right? So I'm hoping that all of you who are all of you who are attending this program have taken the test. That's what I'm telling. So basically, the question that I would like to put before you is more important than attendance is the participation in the quiz on Canvas specifically. This Canvas is one way in which we are trying to ascertain that you are a participant and sincerely, because the email ID and the Canvas login and the Canvas writing the exam will help us to estimate the actual participants, right? So that way we want to see that by tomorrow we want that all of you should take the exam. Please inform your friends also. More important than attendance, we will give more credibility to those who score well. So I was about to show you the certificate hai kya? Ek certificate. So the performance of the certificate we will show you. You'll be happy to know that DST has come forward to provide their logo of both National Quantum Mission and also DST. So we will add that. Presently, we are just showing a previous workshop how we are going to give the certificate. So the exam that you write will carry weightage here. So we will show you that you will be attending, you'll be getting a certificate like this. Hope you are able to see it now. So this is the certificate you will get after completion. So you can look at this and you see that there will be either good or full screen. इधर नीचे रहेगा. हाँ वहाँ full screen नीचे. हाँ. So this is how this will look like. So there you see that his or her performance was good, or the previous thing is satisfactory. If you have a very poor grade, it will be satisfactory. If you have good grades, it will be good. Otherwise, if you are above 9 out of 10 kind of things, you will get excellent, right? So 90% people will get excellent, and somewhere between 50 to 90 will get good, and less than 50 they will get satisfactory. So you please note that these will be the things. These are for other branches that you have looked at. So please ensure that you will take the exam. You will inform all the things. So there are 6 people who will sign. Last will be my name here, where there is principal coordinator, which will be mentioned. So 6 academies will be signing. On top, we will have 4 more logos. That is, one will be DST. MATI is there in between, you can see. So here we will make it to be DST also will be there, and also one more thing that will be there will be IBM and AICT. So 4 more logos will be added to this certificate. So I hope you will try to take it seriously. The Digital India logo is there as this thing. What do you say, watermark. So this will be coming to you. You can take a color printout and keep it, very important. And there is a record that is maintained. So even if you try to make it, so you can see the number which is there, MNITJ/AOT/2025. There is a number that is given. So that number will be unique. So if somebody wants to make a copy of it also, the number you cannot make it unique. So if it is verified, then you will be found that you are trying to, bluff. So please don't try to get into all those things. Anyway, that's not important. What is more important is, taking the exams very seriously. Please inform all your friends to take that. It will be this thing. Yeah, we will make it 40 hours. And what is the other thing? Chat में चले जाओ. इसको बंद करो. 2-week FDP will be mentioned. Okay, 40 hour, 2-week FDP, 40 hour, right? Okay, so we'll do something like that. No, that's not a problem. But actually, this is a 3-week FDP, in fact. Okay, 20 days. So 3-week FDP, we can put it as 3-week FDP, 40 hours, 20 days, something like that we can put, right? So quiz was posted on Sunday, and we have given them 3 days time, 30 minutes. Any time that you start the test, it will be for 30 minutes. So next time also, when you take the exam, we will start at one time. So we will not include it within the 2-hour slot. So maybe on Saturday we'll give you, and you will have time till Sunday evening to or Friday evening we'll give. After the class, we'll give you the exam next Friday. Saturday will be the last this thing. So Saturday contents are taken by IBM. So you will not have exams on that content. So, but then you will have the remaining content. So a detailed mail will come to all of you, in fact, and those who have taken the exam, that's fine. But those who have not taken the exam, please take it seriously. Please inform all friends. You have to attempt all the questions, and I am sure that half of the questions are very straightforward. The other half is moderate. You can look at. So most of you will get 50%. So a brief revision will help you. So the whole purpose is that you should learn. That is more important. So that's where we are, right? Thank you so much. Please tell again how to go on quiz. Okay, so the basic thing is what we are looking at is you need to go to Canvas, log into Canvas. You can see that here when you see Canvas, we'll share once. Share. Once you go to Canvas, you go to quizzes, courses, quantum technology and applications. Click on that, click on quizzes. Once you click on quizzes, you will see quiz 1. It is open till now. We have changed the timing. It will be, we initially announced it till 5 p.m. But now we will make it, we'll close it around 12 o'clock, right? 12 o'clock we'll close it, because madam will discuss tomorrow. Madam will discuss the questions and she will give the answers and clarifications. So before her class starts, we have to close. So we'll close it by 12 o'clock. We'll send an email related to that also. So these questions you can look at. The questions are given below, so you can try to attempt that, right? So this is the first question. Anyway, we are not showing the questions. So there will be only one attempt. We are not giving more attempts. So anybody who is not able to take the exam, please contact us before 2 p.m. for whatever reason. But otherwise, see, because she will be discussing the this thing. So after 12 o'clock, we will mark all those absentees as 0 marks. We'll have one more quiz. So please try to take one more quiz, maybe next Friday evening. That will be the last 21st March. We'll give you the exam, and then 22nd we'll conclude the course. By that time, the certificates will be issued. Right? Thank you so much. Over to Nivedita, ma'am. Credits as of now, this is not yet recognized by any academy, nor it is recognized by what do you call Academic Bank of Credits, ABC. So we are working on that. So immediately it may not be very useful, but if some of the NITs will get it approved in the Senate, right, which is the official academic body, the highest academic body in the institute. If they get that done, then we may issue that from MNIT side or from NIT partner side or something like that. If you are able to do that, we'll let you know. Maybe as the courses proceed, we'll try to look at that, right? Thank you so much.
Thank you, sir.
Yeah.
Okay.
The other clarifications you can ask separately in the discussion forum. We'll clarify. We'll now not waste much time. We'll over to Nivedita ma'am.
Yes. Yes. So I guess the ground for, as of now, don't focus on the exam, just focus on this one. Spend this hour. This is a beautiful discussion. So just spend your time and your mind both into this thing. So classical cryptography is all what we all know. So we'll start with again something that we know, slowly entering into the why, then the what, and then tomorrow we will be doing the how. That is the study. So what is the cryptography? It is a science of encrypting some information. It's basically when crypt means a hidden, vault means or vault, and the suffix graphy means for writing. So it was from the ancient codes or the kind of methods that we are using in cryptography. So it's a method of protecting some information or communication through the use of certain kind of a cipher or codes. Okay, so that only those who are the intended receiver, they only are able to receive it or some will interpret it or process it. No other one than the intended one should be able to get that information. Okay, that was the aim of cryptography. That is the aim of cryptography and communication. Now, encryption is the study or it's a process of converting the plain text, which is nothing but the raw data, into an unintelligible format, or say that is not very important. So something that we cannot decode very easily, which is called the ciphertext. And that process is called the encryption. And encryption is the process of converting a ciphertext to the data itself or raw data or the plain text. That is called the decryption. Okay. And meanwhile, the general process is whenever we have certain data, we actually make it a ciphertext and or through encryption algorithm, then we pass the ciphertext through the channel, and the receiver on receiving the ciphertext passes the data through some decryption algorithm or method in order to get back the original plain text. This is the entire pathway. Some important terminology. Key is the most important ones in cryptography. There are a lot of terms here, which I already put in this slide, but those are very much related to what we already know, or it is very much related to strictly classical ones. So just few of the slides or information I will skip for now, so that once you actually go through it, so either you should be knowing it or it will be a very new classical thing that you can know for cryptography. No way related to or much really that will have some impact on the quantum one. So for this discussion, this hour, I might skip that one. So before that, I'm just telling you. So key is in cryptography, a key is a variable value that is applied using an algorithm to a string or block of unencrypted text in order to produce the encrypted text, or similarly in the decryption algorithm to decrypt the encrypted text. So key is that particular, say, factor that enables proper encryption or a decryption, because data itself is not like complete one. So in order to make the algorithm of encryption and decryption complete along with the data, whether it's a plain data or a cipher data, we also need a key. Okay. Okay. And block cipher is just a process of encrypting and decrypting data. Key is used for encryption, decryption, and same size of input and output. That is the thing. So data plus key is equals to the ciphertext. Initialization vector, it's another one. So initially we start with this one. It's an arbitrary number that can be used along with the secret key to start with. So again, now types of cryptography, EBC mode, CBC mode, all these things are there of encryption. You can definitely, for on your interest, you can go to that, go through all those concepts. This is important one because quantum has different impact on both the types of cryptography. So the first one is the symmetric key cryptography. In symmetric key cryptography, the term symmetric means we only rely on one particular type of key, or the key that we use. Instead of a symmetric key, the base term here is a shared key. That the key that is shared and that is symmetric, that is the same key that we use for both the encryption as well as for the decryption algorithm. It is not different. So first difference is this thing in between symmetric and the asymmetric. And also the very well-known symmetric key encryption algorithms are your data encryption standard, then 3DES or the triple data encryption standard, followed by AES or that thing, advanced encryption standard. Also, there are some advanced algorithms which are used for the symmetric key encryption algorithm, but fundamental thing is that it uses the same key. That is why it's called a shared key algorithm. Okay. Unlike this thing, there is another like domain of cryptographic algorithms, which is known as the asymmetric key cryptographic algorithms. The term asymmetric means something is not in symmetry. So what is not in symmetry is the key itself, which means we use here two different types of keys. So the encryption key and the decryption key, they are different. First of all. So that is how the notion of asymmetric key cryptography has that term has been coined in this way, asymmetric key. Okay. Now also symmetric key cryptography are also some way related to, or it is called a called a private key encryption, whereas or private key cryptography, whereas an asymmetric key cryptography is also known as a public key cryptography. Okay, because a part of the key is there available to the public. And also, say for example, if I have just a quick quiz to all of you, say I have 5 nodes. So, or let me tell the general one. So for symmetric key, if Alice wants to send something, they will be using the same key, right? So maybe A wants to send something to B, so they will be using the same key. B wants to send something to C, another key which is same for B and C, and similarly it will flow in the network. And say for asymmetric key, A want to send something to B. So the general flow is something like, let me just write it down. So A wants to send something to B. So A will be using it what? So some way of this. So both of them will be having some sort of a private key and public. Both of A and B. Public key. Similarly for A also, it should be having a private key as well as a public. That means each of the nodes will be having these combinations. Okay. Now, if A is the sender and B is my receiver, and for a successful transfer of data, how A will be doing the encryption? So if plain text comes on A side, A will be doing encrypt the data, like say encrypt the data with some key based on what key? It is a public key of B. So this is key of pub B. Okay. So instead of this, just a minute. Instead of this, let me just write it. It's thought, I guess it is also there in some slide. Let me mention it. That means, say, just give me a minute. So I'm here. Okay. In case it is there or not, let me check the symmetric key. It should be given. Okay, in this way. Let me also, okay, let me show it here as well. Let me add one slide. Yes. So it works in this way. Say, for example, Alice wants to send something to Bob, where Alice has Alice's public key. So say, for example, let me call it key of, say, A pub. Let me use this nomenclature. And she also has a, sorry, she also has a private key. Let me term it as K prive A prive. Okay, public key and private key of Alice. Okay. Similarly, and Alice is the sender, of course. Bob is the receiver. So Bob also has his own public key, which is, say, for example, KB pub, and Bob's own private key, which is say K Bob private. Okay. Now, in order to send some data, so some plain text will come through encryption. It will become ciphertext that will go to Bob's end. Bob sent from Alice's end. It through some decryption algorithm. It will give the plain text. So this E is basically how I will be doing is, say a data is PT only. So I'll be applying the encryption algorithm E on the PT plain text and the public key of Bob. So K B pub I will be using. With the help of this, I will be encrypting my data. Thank you, Jared. Whoever said there is some issue with this one, the voice, please rejoin. This is all like happening multiple times. So please immediately try to rejoin. Okay. So I will be using you, or say Alice will be using Bob's public key because she can use it because it is available. It's public key. So that is why Alice is using B's public key in order to encrypt the data and then generate the ciphertext through the encryption algorithm. And Bob, on receiving it, so decryption algorithm he will be applying on the ciphertext that he has received and his own private, that is K B prime, in order to generate the plain text. And this entire encryption algorithm or cryptographic algorithm is known as public key crypto system, which is fundamental for RSA, ECC, DSA, only DSA, all these algorithms, which are based on the same concept. All of these are asymmetric key or public key crypto system. Why for this particular thing I am elaborating more? Because it will be used further. Of course, because of that. Okay, and this is the most, what is PT and CT? Can you repeat? Yes, PT is the plain text. That is the raw data. I want to send you an information that I am sick today. But say, or this is a very invalid information. Say, for example, my roll number or my other number, I want to send it to you. All those for like 12 digits. In order to send my other number, I will be, that is my plain text or PT. I will be using some morphing into that. Some sort of logic I will be applying. And say I'm sending you, I'm not, I don't like chow mein, for example, say. And through this kind of encoding I have sent to you. Now, if some intruder or say your enemy or my enemy got this information, which is being transferred from mine end to your end, he or she will not be prioritizing on that information. So that kind of an encoded information is known as a ciphertext. And my other original Aadhaar card number, which I had encoded into the statement that I don't like, say chow mein or anything. So that particular text was the original text, which is called the plain text. Now, of course, through encryption, I should be able to make the original Aadhaar card number into some irrelevant statement. But you are receiving the irrelevant statement, that is a ciphertext, which is irrelevant to all the other users, all the other unintended recipients. You are the intended one. So on receiving them, you should be able to decrypt my irrelevant information and understand or find out the relevant information from it or extract it, which is through the decryption algorithm. And that extracted information is PT, where PT should be exactly equal to the original information that I want to give to you. So plain text is PT and CT is the ciphertext. Sorry. And CT is the ciphertext. And this E is the encryption algorithm. And D is the decryption algorithm. Okay. Now, let me ask you a quick quiz. Say, for example, I have, say I have these kind of 5 nodes, 5 friends in a group want to send some information. Say A, B, C, D, E. So my question to you all is, how many maximum number of thank you, Sai. So how many maximum number of keys I might require for a asymmetric key encryption or a public key encryption versus a private key or a shared key or a symmetric key encryption? My question is, I have 5 friends, okay, who wants to send some information to each other, keeping the confidentiality and integrity, all those things intact. Now, question is, how many keys will be required in a setup where I am incorporating a public key crypto system, and question number B is where I'm incorporating a symmetric key crypto system. Just think before you are discussing whatever you are telling, just think a lot of times, then please answer. But I'm assuming that 5 friends, of course, can communicate. Anyone can communicate in any way to each other. That is, all possible forms of communication are possible in between all the friends. The symmetric, I have 5 friends. So why for symmetric 2 will be required? How you are dividing it? Whatever your logic you are giving, just think symmetric 10. Symmetric 10 or asymmetric? Just see the like theory once. I've told you for symmetric, for in between Alice and Bob, I need just one such combinations or one such key is required. And for asymmetric one, for each of them, I need this one. Right? थोड़ा time ले लो आप सब. Whatever answer you are putting, just before that, think once again. Then please put your answer. This is what my request will be to all of you. Validate your thought process once, then you answer. First of all, can you tell me that, say, if I have the 5 friends, all the number of friends is 5, then how many ways, in maximum cases, how many ways all the 5 friends can communicate with each other? Say for n friends, what will be that logic? If I have n friends or say n nodes in a graph, then how many ways maximum they can be connected? What is the logic? Absolutely, NC2. What is NC2? N into n minus 1 by 2, whatever you call it. So in NC2 number of ways, all of them can be connected to each other. So if I just draw the lines, it will be like this, or A and B can communicate, A and E can communicate, A and C can communicate, A and D can communicate, CB can communicate, CD can communicate, DE can communicate, and DB can communicate. Have I covered everything? I don't think so. So everything should have 4 vertices. Yes, this thing and also this thing. I have done with everything. So if you check it, like B can communicate with all, E can communicate with all. So their degree are 4, nothing but 4. That is n minus 1. So all can communicate. One node can communicate in n minus 1 ways. So n nodes can communicate in n into n minus 1 number of ways. Now, since it is symmetric, the way, and it is an undirected graph, the way I have considered B to be connected with D is exactly similar to the way D is connected to B. So that means it has to be divided by 2. Simple logic. It has to be divided by 2 because it's an undirected graph, which is NC2. So now, see, all these things can be one valid combination for communication to be taking place between these 2 friends. So that means for symmetric, it should be 5C2, that is 10. And for asymmetric, what it should be? Symmetric is fixed. It has to be 10. Many of you has answered 10 as well. I guess few of those who had answered like 1 or 2, just check. I guess like you have not considered all the 5 nodes or some more assumption you are considering. So please consider that at one time we have to consider each of the sender receiver kind of a pair for our calculation. So it can never be only 2 or 1 for more number of nodes. Now my question is for asymmetric or public key, how many number of keys maximum is possible? This one is even simpler. This one is even simpler. What is the logic for this thing? For this public key? What I am telling, key, whenever say Alice and Bob, 5 pairs. Absolutely. So it's 5 pairs of public and private key. Yes, Ravneet. Absolutely. So it has to be 2n, where n is the number of nodes in the graph. So every node will be having one private key, one public key, one pair of public private key. So if it is 5 nodes, they will be having 5 pairs of public and private key, which is nothing but 5 into 2, 10. So it is basically the same number of keys for both the things. Now if you consider 10, say there are 10 nodes. Say there exist 10 nodes. So number of public key required is 20, 2 into n. But this is the public key number. But the number of symmetric key or shared key will be how much? It will be 10 into yes, it will be 10 into 9 divided by 2, which is 45. Numericals are not really that difficult. Just the logic, the fundamental logic should be very clear. Okay. So if I ask you for 10 number of nodes, for 10 number of nodes, what will be the difference in the number of keys required in shared key and the say public key and the shared key? It will be 35. It will be 25. In that way, anything can be given to you. Okay. Also, just one more thing I want to discuss. This is not really very relevant to this purpose, but because we are here in quantum, we are like every time we are considering the cases of 2 to the power n, where n was there in the like classical setup. 2 to the power n is something that we are that is taking place due to superposition. It is exponential speed up. Just a bit of mathematical knowledge that I want to have about all of you or from all of you is, do you really know what is the relation between n and 2 to the power n? If you are well aware of, instead of only that if 2 is given, you have to apply 2 to the power 5 in order to get 32. Instead of only this thing. So I just want to tell you one thing. So just keep it in mind, because in a lot of like algorithms or something, you might require this logic. Let me give you, for those who know, just hold on your patience for some time, because I'm also assuming that there are some students here. So just for sake of their knowledge, let me tell you that see, n number of combinations and 2 to the power n, they are related with some logic. Okay. So whatever is your n is okay. 2 to the power n, just know the expansion or the series expansion of 2 to the power n. So it is nothing but nc0 plus nc1 plus nc2 plus dot 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 up to ncn. Which means 2 to the power n, why it is giving exponential is because out of your n possibilities, either you can choose nothing, or you can choose 1, or you can choose 2, or you can choose 3. Likewise, last cases, you can, out of the n possibility, you can choose the entire set, which is NCN, where NC0 is also 1 and NCN is also 1. And NC1 and NCN minus 1 is also 1. So I hope you know that NCR is equals to NCN minus R. Okay. And for graph theory and a lot of like logic, mathematical logic, we will be requiring the knowledge of this thing, the relation between 2 to the power n and the combination or the series expansion of NC0, NC1, NC2, NCn, which means also something. So it also says that all possible subsets 2 to the power n is all possible subsets of n. We know already if there is a set with say cardinality of n, 2 to the power n is the number of subsets of the set n. So this is how the subsets or that theory is coming into picture. So subset means either from n, I'm not choosing anything. So this is subset. Say subset number 1, this is subset 2. Likewise, I will go on exponentially with the subset 2 to the power of n. This is from when we want to choose subsets from n sets or n elements. Now, if your element is itself n square for certain cases, okay, say for example, I have a word, I have something on a n cross n square matrix. So the adjacent matrix size will be n square. Now I am saying that how many such subsets of adjacency matrices will be there. So similarly, what I want to say to you is that your n itself can be either n or it can be like n square. You have to apply your logic in this way, then n square cn. I just hope I thought of like discussing this thing to you again for the sake of completeness. So it will be like 2 to the power of n square. If I say 2 to the power n c0 plus 2 to the power n c1, likewise 2 to the power n cn, it is 2 to the power of 2 to the power of n, something like that. Okay. Say nc2, then c0 plus nc2 c1. Okay. Likewise, say nc2 cn. Just know this is all possible subsets of nc2. Okay. So this is all possible subsets of, that is 2 to the power of nc2. So this is the formula of 2 to the power n into n minus 1 by 2. So in your set relations and mapping classes, I hope all of you have gone somewhere of these things. I just wanted to add it over here so that you get an idea of the quantum with respect to quantum also, how this thing, how this kind of things are coming. All possible subsets you can encode here. That is why it's an exponential space that you are covering. Okay. And in your NC2, all possible cases where two pairs will be coming, that will be covered. Your NC5, all possible pairs where 5 will be coming, that will be covered. So everything will be covered in this way. Okay. So I just wanted to talk about this. We just discussed it. I hope now we are done with the asymmetric one with a better knowledge and a full understanding. Now the next one is a symmetric key cryptography. This one I already had discussed. So it is like a same key that is used for both of them. Let me not just explain it. And of course, the main drawback of this thing, just highlight the point number 2, that the main drawback of this thing is two parties must somehow know the or exchange the key in a secure way. That this is where the say key exchange algorithms are coming into picture. Can you name any one of the key exchange algorithms? Those who are working on cryptography. Is there any key exchange algorithm that you are aware of? Diffie-Hellman or Diffie-Hellman? RSA is not key exchange. RSA is a public key encryption algorithm. So it's an encryption algorithm, Kiran. Key exchange algorithm and encryption algorithm, they are different. Yes. Diffie-Hellman is a key exchange algorithm. QKD is a quantum key distribution. Okay. Great. Okay. Pause it. So DES algorithm, data encryption algorithm, go through it, just learn the key, that is it. What is role of QKD? That is a part of quantum cryptography. We'll be doing it tomorrow. Theory I'll be mentioning today itself. Just hold on, Hannah. So this is a symmetric algorithm. Go through the details. No issue. And this is AES, which is an advanced form of, okay, from DES, there was triple DES with respect to 3 different possible types of key or key size. And key size is a very important role in anything like in cryptography. I'll explain this one. in the symmetric one already. Just give me a minute. So AES is the third one, which is a strong version than the data encryption standard. It's known as the advanced encryption standard, where there are several multiple rounds of encryption. We start with an initialization vector, then through several mathematical, classical, complex mathematical functions that we apply in order to generate the plain text, in order to convert the plain text to the ciphertext, where size of plain text and ciphertext both are same, and only the encryption algorithm or the methods in the encryption algorithm is different. Okay. DS versus AES, depending on the number of keys. So this is DS AES, and there is also triple DS, which is different than DAS and AES, somewhere in between these two. Mostly the differences here is in form of a key size. So just to give you a glimpse of key size and how the asymmetric one is, how the symmetric one is under threat due to quantum is basically, see, the key size, why it is very important. Say I have a key size of 10 bits, small one I'm talking about. So how many total combinations I can have if I have only 10 bits of key size? How many combinations I can have? Just put it on chat. 2 to the power 2 to the 10. For n bits, it has to be 2 to the power of 10. So this is your search space of security space, whatever it is. So all these things have to be checked in order to perform a brute force attack. A very similar or a very simple cryptanalytic attack I'm talking about. So in order to perform a brute force attack, you actually have to check all the 2 to the power 10 number of combinations. Now you can understand only in 1024 steps you can perform the brute force then? Obviously not. Because why? Because we generally do not prefer a very less number of key size. But one thing you have understood, that if we increase the key size, then it will decrease the chance of brute force attack. Let me write it down. So key size and the chance of cryptanalytic attack somewhere related in this way. Okay, they are not in a positively in a proportional way. So they are in an inverse proportional relationship with each other. That means if I increase the key size, my search space size will also increase. If I have say 1024 bits, so it will be 2 to the power 1024 number of search space. But if I just make it a 1025 bits, it will be 2 to the power 1025. Now do you know, just to give you a quick knowledge check, 2024 and 202 to the power 1025 means how much of difference between these two? If any one of you can tell me. So it's this thing, which is 2 to the power 1024 into 2 to the power 1. So it's a twice of 2 to the power 1024. So jitna search space I have to explore with 1024 key space. If I just increase the key space size by 1 because of the exponential relationship, it will be twice. It is not just by 1 bit, because it is in combination with every possible bit now. So it has now become twice that of 2 to the power 1024. For simple word, if we have 2 to the power 3, it is 8. 2 to the power 4 is basically 16. Where 0, 0, 0 initially it was for 2 to the power 3, it was 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. All these 8 combinations. Now, whenever I make it another bit I'm introducing, say fourth bit I'm introducing, that bit can be either 0 or 1. So it can be 0 and all the initial 8 values will be there. So it's a 0, 0, 0, 0, 2, 0, 1, 1, 1. And for fourth bit as 1, it will be 1, 0, 0, 0 till 1, 1, 1, 1. So likewise, if just by increasing the key size by 1 bit, if the security space increases in doubling the size, you can, I hope you can visualize the impact of the key in cryptographic context. It is very, 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 very important. Okay. More often we make this mistake. To the power 3, we call it okay. To the power 4, we consider. We know because these are small values. So we know that it's 8 and 16. But whenever it is said to the power 2048 and to the power 2049, we often, by mistake, ignore the fact that it is twice that of to the power 2048. Just keep it in mind. That is it. I have discussed this thing. Also here, the same thing. Decrypt, different keys are used and how they are used. All these things we already have seen. So number of keys required is 2n here for n users. Okay. Okay. So M is your plain text. This is your basically encryption algorithm. This is receiver's public key. C is your ciphertext. Ciphertext is received from by Bob. D is your again plain text. F in words is the decryption algorithm. C is the ciphertext that is now acting as an input to the decryption algorithm. This is receivers, that is Bob's private key. Final output is what you started with, the plain text, and what finally we're computing as your plain text to be at Bob's end. There has to be equal. If it is equal, then it's a valid kind of a communication that had taken place. Okay. Now is the RSA algorithm. Every time I mention this thing because this makes me more than happy that I had a chance to meet the Adi Shamir, the ace of RSA, while I was working on a project on quantum random number generator. So I'm very happy to say that he actually validated or gone through whatever concept we built on based on a cloud-based quantum random number generator. So we had a chance to meet him, me and my entire team. So, and we had the chance to meet him at Weizmann Institute of Science, Israel. So it's a great opportunity and a lifetime, something to be remembered lifetime. So yes, so we had a chance to discuss with him that, okay, so RSA is right now not quantum safe. So directly this kind of thing I was explaining in front of him. So that was a very kind of a, what to say, very exciting as well as very threatening moment to me, because I was discussing this thing to the inventor of RSA itself and the one who has discovered all the cryptanalytic things on RSA. Prove that it is very safe, and it has been safe for these 30 years. Right now, due to quantum, there is so much of noise with RSA. But he was more than happy, and he also is a friend of Peter Shor, who discovered that RSA will be under threat by Shor. So this is the essence. Again, this is the essence of academics, and this is the kind of a pleasure when two experts, they actually discuss something or very positively contradict each other's kind of discovery, or this is the essence of science. And I just hope that if once I can have a chance to meet Shore or Grover, that is something that I have in my mind. Let us see if I can get any chance. Okay, so but he also said that, okay, but after Shore, there is no such algorithm that has ever been developed. So that is another kind of a thing that I had heard from him. So RSA algorithm, it was invented by these three uh, kind of great scientists of all time. under these cryptography and cybersecurity space called Rivest, Shamir, and Adelman in 1978. It is the first kind of an asymmetric encryption algorithm and the most widely known asymmetric algorithm. It is used in many of the real protocols which have a real application, like secure socket layer and all these things like TCP. In any application, say for mail transfer protocol, whatever actually you have seen, like most of the security cryptographic protocols, they use this RSA. It's the most widely used algorithm. The idea was based on that, the fact that it is very difficult to factorize a very large integer. So what they have done is they have actually used a very strong, large, big number as a prime number for RSA, where the idea in order to break RSA will be if you can break that integer into its prime components. That was the essence of RSA. Where again, because it is an asymmetric one, so public key consists of two numbers where one number is a multiplication of two large prime numbers, and our private key is also derived from the same two prime numbers. So if somebody can factorize the large number, the private key is compromised. Therefore, encryption strength totally lies on the key size, which gives me some sort of security level. And if we double or triple the key size, the strength of encryption increases exponentially. Okay. Why? Just you have seen it now. Okay. Double means exponentially hoga hi, because only by increasing it by a factor, multiplication factor of 2, if it is making it, by just a linear increase, additive increase, if there is a multiplicative effect. So multiplicative increase will be having a exponential effect for similar logic. And RSA keys can be typically of 1024 or 2048 or say 4096, 8192. These into to the power of 10 to the power of 13 bits long. But experts believe that this can be broken in near future. So which can be broken in near future and which cannot be broken all depends on the power of the quantum computer that we are going to have in near future. This is the RSA algorithm where, just a minute, where it is like we will be having a large composite number n with two prime factors. So we incorporate phi n, which is p minus 1 into, where, okay, let me just also write p n is thought of p and q, okay, and phi n we compute, which is p minus 1 into q minus 1, then private key, factor one of the factors of n, okay, and then in this way we compute the term d into e has to be like 1 mod phi n, okay, that is their GCD or something that has to be, so there has to be like relatively prime or co-prime to each other. This d into e and phi n has to be a relatively prime, because this is 1, or say co-prime to each other. Then this is an encryption decryption thing. Encryption is ciphertext C is equals to plain text M to the power E, where E and D, these are the two things, okay, that I am choosing here. So I'll be choosing E is basically the public key, okay, and D is the private key. So that is why it is a plain text. So ciphertext is equals to the encryption of plain text M. This is your plain text, and this is the key E. It is a public key. And this is what you are putting in C. Similarly, on decryption, Bob will compute the plain text from the ciphertext power the private key of Bob itself, mod N. So it will be again by Euler theorem and all, you will be computing. So if you just compute this, we'll be getting your plain text. Why I cannot do that? Because finding D and E is not really very easy task. Okay, another one is elliptic curve cryptography. This is another approach. It also is based on the public key encryption. Let me just skip it now. You can see it. So it is based on, just remember, it is based on the algebraic structure of elliptic curve over finite fields. Okay. So ECC allows smaller keys compared to non-ECC or non-EC cryptography. And the mathematics here followed is Galois built to provide equivalent security. And they are very applicable for in cases of applications like key agreement, digital signature, pseudo-random generator, and other tasks. Okay. Pseudo-random generator, okay. Just one line for this, because this term you are getting here. So quantum cryptography, just remember this point. Tomorrow we will be discussing, actually I'll put some more time, 5 minutes or 4 minutes on this thing. So quantum cryptography has a huge application, which is a real-time possible application kind of thing in for these random number generators, or say quantum random number generator, because the pseudo random number generator that we have, they are based on the deterministic logic. And also, I guess someone of you asked the question that why RSA is not safe. Just a quick thing, which is very much of theory, that you should be remembering that RSA algorithm, no matter how difficult it is, but ultimately it is a deterministic algorithm. But it was a hard algorithm, undoubtedly, because the reverse mapping was not really very easy. Because from A you can compute P into key, but Q, but from like P, sorry, just a minute. From P and Q, if you multiply it, you can form N. But from N, it is very difficult to get back the factors P and Q. So that is, it is one way kind of a hard problem or one way function. That is why we were relying on this thing, RS. But the ultimately it does not have the power of non-determinism in terms of, if we have a non-deterministic machine, just like the NP, non-deterministic polynomial. So with deterministic algorithm, it is non-polynomial, but with respect to a non-deterministic algorithm, if we have a machine, I have not got your question. Let me, please ask me again also, just after say 5 minutes. We have only 5 minutes left. I will be discussing. I have seen your question, but I have not just understood that what you wanted to ask. Just give a clearer idea of that. So once I have this thing, once I have a non-deterministic machine, which is a quantum machine, RSA will be under threat, because the algorithm itself is a deterministic algorithm. So what we need? We need a non-deterministic algorithm to be absolutely safe from quantum, because a non-deterministic algorithm itself is non-deterministic. So it does not matter that whether we are using a deterministic machine or a non-deterministic machine to solve it. So if some algorithm or if some logic is not based on the mathematical logic, rather it is based on the physical logic or physics at atomic level or say quantum level, we call it inherently random. Unlike a pseudo-random number generator, no matter how strong it is, no matter how much of the periodicity I have introduced into that. Periodicity means after what time interval I might have a repetition of the same number. That means it is a periodic one. That means it is a pattern. So if I increase the periodicity, I might be having some pattern after a long interval. But despite the factor that it can happen after a very long interval, but still it has some potential to get some repetition, theoretical. In quantum also we can see the repetition, but that repetition will not be followed. There is no logic. There is no kind of a machine that can identify or that can just write down some logic that after this much of interval again you are going to see some sort of repetition. That is not possible. Maybe at 0 we have seen a repetition. 0 we have started, say maybe 1 we have seen a repetition, then at 10, then at 12, then at 23, then at say 34, then at 37. So the repetition that can also come, it is so random that you will be not having any essence or any way of understanding that where you are getting a repetition. So we call these kind of a randomness as a truly random number or truly random number. The generator itself is called a true random number generator, but which is a case of a quantum. But the pseudo-random number generators or elliptic curve or all these algorithms may be a complex function. So in Python also you have that np.random function or all these things. All these are based on a pseudo-random number generator where you use a bit complex mathematical formula in order to generate some random integer, a random value, anything which is random that you want to generate. All these are based on pseudo-random number generator, which essentially include a kind of a mathematical function through some deterministic computer. Now, let me replace these terms. Let me have a non-deterministic computer or a quantum computer. Instead of a mathematical function, let it be a unknown physical phenomenon which is occurring at quantum level. What kind of output it will be generating? It is also random number, but that is inherently random number. We call it a information theoretic kind of a security that it is providing. What we call it a information theoretic. Okay. This is the kind of essence. Now, not discuss about this thing. Just a quick discussion that NIST or National Institute of Standards and Technology, they already have declared, and US government also have approved that everything right now can be under some sort of threat. Everything means every sort of cryptographic algorithm, but definitely their level of threat is not same. So there are different levels of threats associated with the existing classical cryptographic standards that can arise due to quantum. And these are just the classical algorithm details, not related to threat part. Let me go back to the threat thing. Diffie-Hellman key exchange algorithm. Okay. Just a trait one. So only let me just explain these two slides to you. So just you see the known threat of quantum algorithms is, instead of the slide, let us just understand it. First, let us understand this thing. So the asymmetry. So what I have just said, that threats can happen to both what? Either to public key or say asymmetric key, which is for say RSA, ECC, TSA, and all these public key or asymmetric algorithm, or it can also happen with the shared key or symmetric key. What are the algorithms? DES, the official kind of that, D3, DES, AES, all these algorithms. Now, Schwab already shown that, and all these algorithms are based on the core of all these crypto systems are based on integer factorization or discrete logarithm. And integer factorization and discrete logarithm problems are like a vice versa model. So they are polynomial time reducible from one to another. So that is basically the same problem. And Shor's algorithm already is proven to be broken. So these algorithms are proven to be broken, or in near term, they will definitely be broken. So they are under more threat, undoubtedly, because their model uses these two things. What are the two things? Either, where can I write? Either integer factorization. Don't worry, I'll be putting 5 more minutes on tomorrow, starting on this. Then we'll slowly enter. There will be a good transition. Don't worry about that. And the discrete logarithm. But unlike your shared key or symmetric key, they do not believe in that. If their algorithm is the way they are built on, that is very kind of a difficult, or in say not really relying on anything related to the integer factorization technique or any of the siblings of that problem. Okay, and due to several encryption rounds, they are really very strong and fast as well. But the thing is that now comes another algorithm which we already love. That is a Grover search algorithm. So what Grover is claiming here that, okay, so you might not be using anything with the integer factorization, so short might not be able to break it. But how many key size you are having? Say DES is telling that I have a 128 bit of key size. Then it tells that, okay, you have 128 bit key. Okay, that means your search space will be of how much? 2 to the power 128. Now, if I'm an intruder, I have to search your entire search space in order to do a brute force attack or perform any smart cryptanalytic attack. Then in worst case, if I have a classical machine, why are you so happy? Because 2 to the power 128 is very large number. Answer is yes. So developer is telling yes. Now as an intruder, I'm telling that don't be so much of happy because I have a quantum computer. So initially, why you were so happy or you were so relaxed? If you have n data, in worst case, in classical search, if it is absolutely random or it is not sorted, then it should be taking 2 to the power 128 bit of time or this much of query, whatever you say it. Complexity is itself 2 to the power 128 minus 1 in a linear. Okay. But an intruder, if he can use Grover search and has a quantum computer, then how much of time he will take? He will take for n if it is root n. So for 2 to the power 128, it will be root over of 2 to the power 128, which is 2 to the power of 128 to the power half. 2 to the power n by 2, we do it. So cancel it out. So it is 2 to the power 64. So this is again a mind-blowing kind of a thread that quantum is putting. So in short, whatever be your key size, whatever be your existing key size, and based on that, whatever applications you have built, my claim is I can immediately reduce your search space by a factor of 2. Immediately, if I use Grover search. So it is what it is doing. It is kind of a weakening the symmetric key algorithms. In short, again, just an end note. What quantum is doing with the asymmetric key, it's kind of a broken or very near term, it will definitely be broken. So it's a gone case. So we cannot do or cannot go further, do anything with the asymmetric key encryptions. Some alternative solutions we have to think of. But for symmetric key, the effect is not as worse as asymmetric, but it is still under threat. Why? Because it is weakening it. And not only in some linear terms, rather, it is dividing the search space exactly in half. So that is also a significant kind of a threat that it is put because it is weakening. Right now, we thought that AES 256 or AES 512 is almost secure. 256 is kind of half secure, but AES 128 is really under threat. And how we are telling it again due to the discovery of the quantum computers. Okay, so let me pause here or stop here. It's 4:05. We are already out of time. So tomorrow I will start exactly from this point and enter into that. Since asymmetric ones is not going to work further or anymore, is there any alternative solution or what is our thought process to find out an alternative solutions and what is the solution? Suppose that we will see that what if instead of any solution, what if key purely on quantum copy? We will entirely convert it to quantum. That is quantum cryptography. We'll see these two topics in our last class or like your last class with me, that is on tomorrow. Okay, let me stop sharing. So today, so we will end here. Okay.
Thank you, Nivedita ma'am. Thank you for your time, and we are winding up today here. And please note that